In this experiment, we're going to test the accuracy and precision of a device designed to accurately and precisely deliver 5 milliliters of liquid into a container. This is called a volumetric pipette, and they're used regularly by chemists to deliver specific volumes. This particular volumetric pipette is designed to deliver 5 milliliters. In this experiment, you will determine the volume of water transferred using the volumetric pipette by mass. Over several trials, you will transfer 5 milliliters of water from the beaker into an Erlenmeyer flask and record the mass. Knowing the mass of the empty flask and the mass of the flask after each subsequent trial of water has been added, you will subtract and find the mass of the water for each trial. Then, using the temperature of water and the density, you will determine the volume of water transferred for each trial. In this way, by doing the experiment repeatedly, you will test the precision of the experiment. Since this is a 5 milliliter volumetric pipette, you will test the accuracy because you know it should deliver 5 milliliters of water. You will then use that as your standard to determine your percent error. In order to use a 5 milliliter volumetric pipette, you're going to need to use a pipette pump. A pipette pump is designed to draw liquid into a pipette. This is done by simply scrolling the wheel and sucking the water up into the pipette. In an ideal world, you can use the pipette pump to exactly fill the volumetric pipette with 5 milliliters of liquid. However, it's very rare that these actually work exactly as planned. So it's much better to actually draw in more liquid than you need and then drop the volume of the liquid until you have exactly 5 milliliters. And I will demonstrate that for you now. As mentioned, a 5 milliliter volumetric pipette has just one job: to transfer 5 milliliters of liquid into another container. You'll see here that it has what's called a calibration line. The calibration line is the only marking on a 5 milliliter pipette. This is the level at which you want the liquid to be in order to deliver 5 milliliters. Now that I have all the tools that I need to use the volumetric pipette, I simply want to place the pipette into the beaker and place the pipette pump on top. Now, before I start to draw liquid into the pipette, it's very important that I lift the pipette slightly off the bottom of the beaker, for the very simple reason that if it's exactly on the bottom of the beaker, you're blocking the hole where the water comes in. Once I have the pipette lifted slightly off the bottom of the beaker, I want to simply scroll the pipette wheel and draw water into the pipette. Notice that I've drawn water above the calibration line. In order to continue, what I want to do is very quickly remove the pipette pump and place my thumb on the top of the pipette to keep the liquid from flowing out. Once you've reached the calibration line, you want to transfer the pipette from the beaker into the Erlenmeyer flask and then remove your thumb. Once you remove your thumb, the liquid will flow out of the pipette and into the flask. You'll notice that it flows out quite slowly. This is because it has a very small hole in the end. This is designed on purpose so that you can actually stop at the calibration line. You'll also notice another factor that happens when because there's such a small hole at the end of the pipette is a small amount of liquid is remaining in the pipette. The pipette is calibrated so that this small amount of liquid is taken into account. It's very important that when you're using a volumetric pipette, you do not use the pipette pump to blow the liquid out, because in that case, you will not have the small amount of liquid remaining in the tip. In order to prepare the solutions that you're going to use for the titration, you're going to need 5 molar sodium hydroxide solution and a 10 milliliter graduated cylinder. The first thing you're going to want to do is transfer 2 milliliters of the sodium hydroxide solution into the graduated cylinder. To do this, I'm going to use a pipette. Once I've added approximately 2 milliliters of sodium hydroxide solution into the graduated cylinder, I want to hold the graduated cylinder with my hands and move my eye down to the level of the graduated cylinder and remove sodium hydroxide so that I have exactly 2 milliliters. Next, I want to quantitatively transfer the 2 milliliters of sodium hydroxide solution into the volumetric flask. A volumetric flask is very similar to a volumetric pipette in that it has only one job. This volumetric flask's job is to hold 100 milliliters of solution. And just like a volumetric pipette, it has only one line. This line is the 100 milliliter line for this particular volumetric flask. To quantitatively transfer my sodium hydroxide solution, I first want to pour the sodium hydroxide solution into the volumetric flask. Next, I want to use a few small portions of water to rinse the flask completely of all of the sodium hydroxide solution so that I can be sure that all of the sodium hydroxide is in the volumetric flask. Once you've transferred the sodium hydroxide solution and the several rinsings of water into the volumetric flask, you next want to fill the flask with water. If you're going to do this with a pipette, you'll notice very quickly that this will take you forever. You don't want to do it with a pipette. What you want to do is you want to fill the solution, fill the flask, up into the neck by pouring. Then once you're in the neck of the flask, but still below the calibration line, you want to use the pipette to get the exact amount of solution that you need. This is the most efficient way to do this. So in order to do this, I'm going to pour the water up into the neck of the flask. Now once I'm relatively close to the calibration line, I want to use a plastic pipette, which you could find in the lab, and simply move my head to eye level and fill the flask such that the bottom of the meniscus is exactly at the calibration line. Finally, we need to mix the solution. 5 molar sodium hydroxide is far more dense than water. So if I were to use this solution now, it would not be uniform throughout. To do that, you simply place the stopper on the flask, place your fingers over the stopper to make sure that it doesn't fall over, invert the flask, and shake. You repeat this process several times, making sure to hold the stopper until you have a solution. Now that we've made our sodium hydroxide solution, we need to prepare our Erlenmeyer flask for the titration. In a titration, the acid always goes in the Erlenmeyer flask. We already prepared a 0.2 molar hydrochloric acid solution as is stated in the lab manual by adding 3.5 milliliters of hydrochloric acid to about 50 milliliters of water. We then swirled the solution to make sure that it's uniform. We want to use a 5 milliliter volumetric pipette to transfer 5 milliliters of the hydrochloric acid solution into the Erlenmeyer flask. You've already used a transfer pipette previously, so we will do the same procedure now and draw the hydrochloric acid up above the calibration line, bring the solution to eye level, and stop at the calibration line. We then transfer the solution into the Erlenmeyer flask with which we're going to use to perform the titration. Notice that again, I'm allowing the solution to come out by gravity and I'm not blowing it out using the pipette pump. Finally, what I want to do is use a squirt bottle of water and squirt down the sides of the Erlenmeyer flask so that all the solution is in the bottom. I then swirl the flask, and now this is ready for a titration, except for I need to add indicator. Notice that it doesn't matter how much water I add to the flask, I just want to rinse the solution down a little bit because the water doesn't have any acid in it. And in a titration, I'm going to react the sodium hydroxide and the hydrochloric acid. Since the water doesn't have any hydrochloric acid in it, I can use a reasonable amount. This is not to say you should fill the entire flask, but a reasonable amount of water is fine for your rinsing. Finally, I want to add a couple drops of phenolphthalein indicator. With many things in life, more is better, but phenolphthalein is not one of those things. 1 or 2 drops is plenty. Now that we have our acid in our Erlenmeyer flask and we've added indicator, you're going to do this over 4 trials, but here I'm just going to demonstrate with 1 trial. We need to use a burette in order to do a titration. A burette allows us to measure how much of, in this case, sodium hydroxide is used in the reaction. However, before we can use the burette, we do need to clean it, and that's very important. You're going to need a few things to do this. You're going to need a beaker for waste. You're going to need a beaker for your 0.1 molar sodium hydroxide that you prepared previously, and you're going to need a beaker of water. You're also obviously going to need a burette, and to use the burette properly, you should also have a funnel. Notice that a burette has a stopcock at the bottom. When a burette stopcock is perpendicular to the burette, it is closed. When it's parallel, it is open. For right now, I want to make sure that the stopcock is closed. Before and after you use a burette, it's always important to rinse it with water. We rinse it before to make sure it's clean before adding our sodium hydroxide solution. We rinse it after to make sure that there's no remaining sodium hydroxide solution. Remember that sodium hydroxide solution contains sodium hydroxide, and if the water evaporates, that'll leave solid sodium hydroxide in the burette. The burette has a very tiny hole at the end and it can become easily clogged, so it's always important to rinse a burette before and after we use it. To rinse a burette with water here, what we're first going to do is lower the burette down. For many people, you would be reaching up over your head in order to pour the solution into the burette. In this case, we're just going to rinse it with water. To lower the burette down, we simply put the burette at the edge of the table and then lower the burette so that it's an appropriate level to work with. We also want to use a funnel in order to fill the burette. It's very important that when we're adding a little bit of water to the burette to rinse it, that we hold the funnel up so that it's slightly above the top of the burette. If you leave the funnel down like this, you can get an airlock, and believe it or not, you can actually fill up this funnel and none of the solution will actually go into the burette. In order to avoid that, we simply hold the funnel up a little bit. We want to rinse the burette with about 3 portions of 5 milliliters of water. This doesn't need to be exact. So I'm just going to take my beaker of water and I'm going to add in about 5 milliliters. Then what I want to do is simply open the stopcock at the bottom and allow the water to flow out. So you can see this on camera. I'm going to go ahead and pull the burette back up, although when you're doing it, this probably isn't necessary. I'm then going to take the waste beaker and flow the water out of the burette and into the waste beaker. Once the burette is empty, I'm going to close and repeat this process 2 more times. Now that I've rinsed the burette 3 times with water, I want to rinse it with some of my sodium hydroxide solution. Right now, the burette is wet, and that water will dilute the sodium hydroxide solution. In order to avoid that, I want to rinse the burette with 3 portions of sodium hydroxide. In this case, 1 to 2 milliliters is plenty. It is a bad idea, bad practice, to pour from a volumetric flask directly into your burette. It is a much better idea to get a clean and labeled beaker. It is essential that this beaker is dry so that we don't dilute the sodium hydroxide solution. We simply add some of our sodium hydroxide into our clean, labeled, and dry beaker and use that to rinse the burette with 2 to 3 milliliter portions. Once the burette has been rinsed with 3 portions of water and 3 small portions of sodium hydroxide solution, we're going to want to fill the burette up in order to do the titration. A burette is used to measure the volume by difference of sodium hydroxide solution used in this titration. In order to do that, I'm going to first lower this down so that it's the appropriate height for me to pour into it. Then holding up the funnel, I'm going to add sodium hydroxide solution to the burette such that I have above the 10 milliliter graduation on the burette. This will ensure that I have enough sodium hydroxide solution to do the titration. One common thing that happens when using a burette is that when you fill it up, there's an air bubble still in the tip of the burette. It is essential that you remove this air bubble before you read the initial volume of the burette. If you fail to remove this air bubble, you will fill this with liquid and lose that volume, and it will cause imprecise results in your titration. To remove the air bubble, you simply, using the waste beaker, open the burette for a second or 2 and make sure that there's no air bubble present. Now that we've filled the burette up and removed the air bubble from the stopcock, we need to take the initial burette reading. To do that, you generally want to use something white. In this case, I have a white paper towel. You could use a piece of paper or anything else that's white because it provides contrast and allows you to be able to read the numbers more clearly. Here you can see that our volume measurement is between 8 and 9 milliliters. It's very important that we read it from the top down. So we're going to read this as 8 point something milliliters and not 9 point something milliliters. So we read a burette from the top down. You'll also notice that we have tenths graduations on the burette. So, since we have tenths graduations and we need one estimated digit, it means we have to estimate the hundredths place. Said another way, our Burette reading should have 2 decimal places, and all Burette readings must have 2 decimal places, even if the last decimal place is a 0. In this case, we would read this as 8.72 milliliters. Now that I have the initial Burette reading, I want to take my Erlenmeyer flask containing the acid and the indicator and place it under the Burette for the first time. Notice that I never put this under the Burette before because I didn't want to accidentally add any base into the Erlenmeyer flask, which could cause some errors in the titration. Also notice that I have the stopcock placed on this side of the Burette so I can use it with my right hand. I'm right-handed, and I strongly recommend that you use your dominant hand to control the stopcock, and then you use your other hand to swirl the flask. So I need to swirl the flask and control the stopcock at the same time. I want to begin by slowly adding some of the base from the Burette into the Erlenmeyer flask while swirling. You'll notice that if I stop swirling for a second, you can actually see some pink color in the flask. This is a good way to know that you've added some indicator. I then want to continue the titration in such a way that I'm adding more and more base, and you'll notice that the pink color begins to persist longer and longer as I reach the end point of the titration. My goal is to add a single drop of the base and have the solution turn and stay pink. In order to do that, when I get close to the end of the titration, I need to go very slowly. As I get closer and closer to the end of the titration, the pink color will persist longer and longer. At the end of the titration, I want to add just a single drop of the sodium hydroxide solution and have it turn the solution in the Erlenmeyer flask pink. This is how I know that I performed a proper titration. As you can see here, a single drop of the base causes the solution to turn and stay pink. This is the end point of the titration. Now that the solution has turned pink and the titration is complete, we want to read the final volume of the titration. To do that, we again add our white paper and we read it to 2 decimal places. In this case, reading from the top down, we find that this is 18.79 milliliters. There's a couple other things that I would like to show you. The first one is that how important it is to make sure that the titration ends at a single drop. Here I'm going to show you what happens if I significantly over titrate the solution. So here I'm adding in 20 or 50 extra drops to show you what happens visually to the solution. You can see here I still have a pink solution. You can't easily visually distinguish this as an over titrated solution. Therefore, it's very important that when you're doing your titration, as you reach the end point, you make sure you finish the titration with just a single drop of sodium hydroxide solution. This takes practice and patience, and this lab is your opportunity to do those things. Now that you have completed the titration and have the initial and the final Burette reading, it's time to clean up. We have designed this experiment so that the concentration and volume of the sodium hydroxide and hydrochloric acid solutions will exactly neutralize each other. So you should mix all your waste from your 4 titrations, we only did 1 here as an example, and all your leftover solutions into 1 container. You will then have approximately 0.2 molar sodium chloride or salt water. This solution can go down the sink. Although it may look a pink color, there is almost no phenolphthalein indicator, as it is very dilute in these solutions. Also, as far as cleaning, you need to make sure that you thoroughly clean the Burette. To do that, you want to use your waste beaker and drain any excess sodium hydroxide solution, which again would be combined in the waste. Once the solution has been drained, you want to use water and rinse the Burette with several portions of water to ensure that there is no sodium hydroxide solution. Sodium hydroxide will clog burettes and ruin them, so please make sure that you thoroughly clean your burette so it's ready to go for the next person. In this part of the video, we're going to go over the data analysis. So you'll notice here that we have the mass of the flask before adding water. Then we add the 5 milliliters of water, and the mass of the flask goes up by roughly 5 grams. And the reason for this is the density of water is 1 gram per milliliter, so 5 milliliters of water from the 5 milliliter pipette should be about 5 grams. And this is part 1 of the experiment where we were simply pipetting 5 milliliters of water. What you'll also notice is that the final mass is the new initial mass. Said another way, we don't empty out the flask every single time. We simply use this as the new initial mass, then we add 5 more milliliters. This is the new initial mass, and then we add 5 more milliliters, and then same and repeat. And you'll notice it goes up by about 5 grams each time. Now what we want to find is the mass of the water, the volume of the water. And in order to find the volume of the water, we do need to use the density. To find the density, you need to measure the temperature of the water. In this case, we measured at 19 degrees, but you're going to measure the temperature of the water in the lab and then use the table in the lab manual in this experiment in order to relate that temperature to a density. So in our case, the temperature of 19 degrees is 0.9984 as the density. So I'm going to simply plug in 0.9984 as the density right underneath the temperature, but it doesn't honestly matter where you plug it in. That's just where I'm going to plug it in right here. So now we have the density of the water. Now in order to find the mass of the water for each trial, we want to subtract the mass of the flask and the water is added minus the initial mass. Note that because again we're adding 5 milliliters each time, the initial mass is here, but it goes up by 5 grams, so we can just subtract. This keeps us from having to reweigh the empty flask every time. Keep in mind the empty flask will have a different mass every single time because it'll have different amounts of residual water in it, so it's much easier to just add 5 more milliliters every time. Remembering that to get Excel to do math, we click the equal sign. Then we're going to click on the final mass minus the initial mass. This should come out to be approximately 5 grams, again because the density of water is very close to 1, so 5 milliliters of water should be roughly 5 grams of water. I'm going to simply pull that through, and you can see we added about 5 grams of water in each case. Now we need to find the volume of the water. So if you'll recall, density equals mass divided by volume. If we cross multiply here, we find that volume times density equals mass. Then we divide by density. We find that volume equals mass divided by density. So the volume equals the mass divided by the density. So we want to take the mass of the water and we want to divide by the density of the water. Now, there's a small problem here. The small problem is that the density is in only one cell. So if I drag this down, it's going to take C3 divided by I guess it'll be E4, okay, and we don't want that to happen. So to prevent this from dragging, we want to put dollar signs around it. Now, you can either just manually type in a dollar sign here and a dollar sign here. This locks E, this locks 3, okay. The other way you can do this, I'm just going to delete this, is click this and then click F4 on a PC, and that puts the dollar signs in there for you. Now you can hit enter. Then you simply drag this down. Note when you do it this way, all of these things are around 5, and they should be. They should be slightly higher than this. Why? Because we divided by a number very close to but slightly smaller than 1. And if you divide by a number slightly smaller than 1, it goes up a little bit. So 4.9911 becomes 4.9999. So that's basically that. All right, watch what happens if we forget the dollar sign. Sorry, I clicked the wrong one. Here, now when I drag it, what happens is we get divide by 0. Why? Because that's trying to divide by what's in this cell, and there's nothing in that cell. So make sure that when you do this with the E3, you do put the dollar signs, or just hit F4, and then you drag, and you'll know if you did it right, because you'll get numbers. Now we want to calculate the average. Remembering that Excel knows how to calculate average. Always equal sign, average, open a parentheses, select your data. Okay, oops. Then the RSD is the standard deviation of this data. Okay, make sure not to include the average, so just the first 5 data points, divided by the average, which we just calculated, times 1,000. Okay, and this gives us the standard, the RSD of this data, and then the percent error. So the percent error is the difference from the accepted value from the experimental value. In this case, we're going to use the average. So the percent error, as you've done before, is equal to the accepted value minus the experimental as an absolute value, because we don't care if it's higher or lower, divided by the accepted times 100. So in this case, the accepted value is 5 milliliters. So to do absolute value, again, we type equals to get Excel to do math. Absolute value is ABS. We're going to take the average minus 5, or 5 minus the average. It doesn't matter, okay, if you prefer to do it like I did it here. 5 minus the average, because it's an absolute value, it makes no difference, divided by the accepted value, 5, and then because it's a percentage, we multiply by 100. So this RSD is relatively low, which tells us that the pipette volume is precise. That's to be expected. That's what a pipette is for. It's to precisely transfer 5 milliliters of water. You can also see the percent error is very low. It's less than 0.1%. That is also expected from a volumetric pipette because, again, it's designed to transfer 5 milliliters every single time, so the RSD is low, and it's designed to transfer exactly 5 milliliters, so the percent error is low. So these two values should be relatively low. If you have an issue here, you might have to do another pipette, because it might be, some kind of, there's some kind of human error, if you will, with your trial. So that is the data analysis of the first part, and now I'd like to move to the data analysis of the second part. So in the second part of this experiment, we reacted hydrochloric acid with sodium hydroxide solution to form NaCl in water. And we did this as a titration, so there was an indicator. Said another way, when the moles of HCl and the moles of NaOH were exactly equal, we reached the equivalence point, the solution turned pink. So if you'll recall, what you titrated was 5.0 milliliters of HCl. Then for the NaOH, you put this in the burette. To find the volume of NaOH, you're going to take the final burette reading and subtract the initial burette reading. That's the difference to tell you the volume of NaOH. But we also know that this NaOH is 0.1000 molar solution. Our goal is to find the molarity of this. All right, we want to find the molarity of the HCl. So I'm going to do this on paper for the first trial, then I'm going to show you how to type it into Excel, and then once it's in Excel, we're just going to drag down. So to find the volume of NaOH, we take the final burette reading minus the initial burette reading. Note that, I changed this should be an 8. Note that the final burette reading of one trial is the initial burette reading of the next trial. Note that this works until you get to about, 35-ish milliliters. If your initial reading is 35 milliliters, in this case, you would not want to do the next trial, because in that case you may run out of NaOH. The burette only holds 50 milliliters, so if you run out of NaOH, that is a problem. So you want to make sure that your initial reading is below about 35 before you do the next trial. Note that for different titrations, that's a different value, okay? 35 sometimes is way too low to start a titration, because if the titration takes 35 milliliters and you only have 15 milliliters in there, you're not going to be able to do it, right? Because if you're at 35, you only have about 15 left, because it goes to 15. Oh, it goes to 50, sorry. So that's basically that. It's not a one size fits all, that always if you have more than 35 milliliters, you're good. It's just in this case, since it takes about 10, if you have about 35, you're good. All right, so now we know that this one took 9.83 milliliters. So now our goal is to find the molarity of the HCl. So plan of attack. What's our plan of attack? Well, we're going to start with the liters of NaOH. What can we find with the liters of NaOH? Well, we know the molarity of the NaOH, so we could find the moles of NaOH. Once we found moles of NaOH, we could find moles of HCl. Remember, to convert from moles of one compound to moles of another, we always use a balanced chemical equation, and we have a balanced chemical equation right here. Then if we take the moles of HCl and we divide by the liters of HCl, this will give us the molarity of HCl. Note that this isn't a dimensional analysis conversion. This is creating a new unit, molarity, but in this case, molarity is the unit that we want. So that's the unit we want to create because we're trying to find the molarity of the HCl. So how are we going to do that? Well, in this case, we need to convert the volume in milliliters. This is the 9.83 milliliters that I just found right here into liters. So we have to divide that by 1,000. So it's going to be 0.00983 liters of NaOH times. We want to convert from liters to moles. If you recall from the stoichiometry section of the course, to convert from liters to moles, we always use a molarity. This means there is 0.1 moles per liter. Said another way, there are 0.1100 moles of NaOH per 1 liter of the NaOH solution. These go on, liters goes on the bottom, so it'll cancel out, and we end up with moles of NaOH. So this is the molarity of number of moles per 1 liter times. We now want to convert from moles of NaOH to moles of HCl, and as I mentioned a minute ago, we use a balanced chemical equation for this. So it's going to be 1 mole of HCl, all right, because we want HCl, and then we want NaOH to go, so we put 1 mole of NaOH on the bottom. So always the thing you want to cancel out on the bottom. I'm going through this relatively quickly because you've done this a lot of times before. Now we need to convert from moles of HCl to liters of HCl. So we put a unitless 1 here. This simply moves the moles of HCl over. We can now put the liters of HCl on the bottom. Now remember that you use the same pipette that you used in the first part to pipette in 5 milliliters of HCl. Said another way, you use 0.00500 liters of the HCl solution. Now to solve this, you multiply by the top, divide by the bottom, multiply by the top, divide by the bottom, multiply by the top, divide by the bottom. But if they're ones, you can skip them. If you prefer to put it all in, that's totally fine. But instead of doing this with a calculator, we're going to do this with Excel. Why? Because we're going to need to do this 4 times, and it's going to be much easier to do it 4 times by just dragging down than to type it into our calculator 4 times. So equals, the first thing we need to do is we need to convert the volume of HCl into liters. So we need to take that volume in milliliters and divide it by 1,000. Now we're going to have this value right here. So this is just 9.83 divided by 1,000. And if you look, you can actually see that that's the exact same value. Now, you don't need to do that, all right? So I'm just going to re-click on this. Now what do I want to do? I want to multiply by 0.1 and divide by 1. Well, since I'm multiplying or dividing by 1, I don't really need to put that in there. So I can just times 0.1 000 if you like, but that's not going to make any difference in Excel because Excel doesn't do sig figs, so it doesn't matter how many zeros you put. You could just put 0.1 or you could put 0.1000. It doesn't matter. All right, now we need to divide by 1. I don't need to do that because any number divided by 1 is itself. Multiply by 1, I don't need to do that because any number divided by or multiplied by 1 is itself. Divide by 1, same thing. Multiply by 1, same thing. Divide by 0.005. So I want to take this whole thing and divide by 0.005. Okay, and when we click that, we find that it is 0.1966 molar. So this is the molarity. It should be approximately 0.2 molar. Note that I want to show you how to do this a different way. If I take this and divide it by 1,000, that'll give me the milliliters, okay? Or excuse me, the liters, like I showed before. Now, if you prefer, you can do times 0.1000 over 1. So I just plug this whole value in, times 1 over 1. So I'm just going to put in parentheses, 1 divided by 1. It's not necessary to put in parentheses, but I'm going to do that. Times 1 over 0.500. So 1 divided by 0.00500. Okay, that's the 5 milliliters. And then close the parentheses. So basically I plugged in each of these things in parentheses and then I hit enter. You notice that you get the exact same answer. So Excel, if you ignore the ones, you put the ones in, it doesn't really matter. Excel can crunch the math. It doesn't penalize you for putting extra numbers that you don't need in it. So just put it on however is convenient for you. Then, as always, we highlight our data, click the little green box, and drag, and we end up with all of these molarities. And you'll notice that we titrated the same thing, so we want to have all the same molarities. We're going to find the average, open a parentheses. I don't know how the caps lock got turned on, but I'm just going to highlight my data, find the average. Okay, something went wrong there. Let me try again. Equals average. I think I might have added an extra letter in there. All right, then I'm going to hit my data. Now you can see the average. That looks reasonable for those data. All right, they're all pretty close together. Now I'm going to find the RSD, which is going to be the STDEV, which is the standard deviation. Don't highlight the average, only of your data, divided by the average, which I just calculated, times 1,000, and we'll get the RSD and PPT. In this case, I get 7.12. When you're doing this in the lab, you should have an RSD of less than 25. If you don't have an RSD of less than 25, your TA may ask you to do additional titrations. So it's really important to go slowly and get it to turn pink at that last drop. So thank you for watching this data analysis video. I hope that you found it helpful.